In this video, we are going to know silicon and other semiconductor materials. We need to know a concept of energy bands. Band gap is an energy range where no electron states can exist, so the electrons can stay in either conduction band or valence band. There are three types of materials in terms of conductive abilities: insulator, semiconductor, and conductor. An insulator is a type of material that does not conduct electrical current under normal conditions. Valence electrons are tightly bound to the atoms. Therefore, there are very few free electrons in an insulator. A conductor is a kind of material that easily conducts electrical current. The best conductors are single-element materials, such as copper. There is only one valence electron very loosely bound to the atom. These loosely bound valence electrons can easily break away from their atoms and become free electrons. A semiconductor material falls between conductors and insulators in its ability to conduct electrical current. Current flow in semiconductor devices can be controlled by an external force, such as electrical potential. So it can be designed to be a switch. If a sufficient amount of current is flowing in the device, the switch is closed. Otherwise, it's open. The switch can be explained as binary 1 or 0, which is the basis of modern computing. Intrinsic semiconductors are perfect semiconductor crystals that have no impurities and lattice defects, such as pure silicon. These elements are found in group 4 of the periodic table. When an element having 5 valence electrons from group 5, such as arsenic or phosphorus, is added to group 4 element, such as silicon, there are more valence electrons available to form a covalent bond with silicon. One of the 5 electrons is free to move and becomes a free charge carrier. This method is called doping. The extrinsic semiconductor has an extra electron, such as silicon doped with arsenic or phosphorus. It is called N-type material. In contrast to an N-type semiconductor, when a group 3 element, like boron or indium, is added to the silicon, the impurity atom is 1 electron short of 4 valence electrons to form a covalent bond with silicon. This deficiency of an electron creates an extra hole in the material. In this case, the hole is a free carrier, and the semiconductor is said to be a p-type material. The compound semiconductors can be a mixture of the 2, 3, or 4 elements. Some examples of compound semiconductors are gallium arsenide, indium antimonide. Silicon is the most widely used semiconductor material in microelectronics because of its material properties and also because it can easily be extracted from naturally abundant silica. The atom structure of silicon and germanium are shown. Both silicon and germanium have the characteristic 4 valence electrons. The valence electrons in germanium are in 4th shell, while those in silicon are in the 3rd shell, closer to the nucleus. This means that the germanium valence electrons are at higher energy levels than those in silicon, and therefore require a smaller amount of additional energy to escape from the atom. This property makes germanium conductive at high temperatures, and this is a basic reason why silicon is the most widely used semiconductor materials. Compound semiconductors are widely used in high-speed and optoelectronics applications. Some have high electron speed and high mobility. However, the cost involved in manufacturing the compound semiconductors is much higher than for silicon. As such, the efforts of the semiconductor industry have been primarily focused on developing the silicon technology since the invention of the transistor. If you like this video, please like it and subscribe.